All right, so last week we talked about linked lists, covered the first data structure of our data structure trifecta coming up here. Linked lists, I said everything that you needed to know about linked lists on Monday. That's everything you needed to complete the objective. And we spent 2 extra days just diving a bit deeper into linked lists. We talked about stacks, we talked about queues, and we went through a memory diagram, and then talked about test cases last time. Now we want to do the same treatment for binary trees. We're going to talk about what a binary tree is today, what the whole thing is. Wednesday we're going to introduce binary search trees, an application of binary trees, and then a big old memory diagram on Friday. This week in lab is the second chance lab. Since for some of you this will be your first second chance lab, I just want to talk a little bit about the structure, just in case if it didn't apply to you last time, there's no real reason to listen. But if you didn't pass the quiz and interview last time, 2 weeks ago, this is your chance to make those up. The structure will be the same. It'll be a flashback of 2 weeks ago. The interview and quiz, the TAs will call your name for the interviews, the same old role. If you did not pass the quiz, but you passed the interview, you're going to show up just to take the quiz. If you pass the quiz, but not the interview, you're showing up just to take the interview. If you pass both the quiz and interview, you're not showing up at all. We got none for you in lab. There's no reason for you to be there. Just take the week off of lab. If you only need the interview, for those of you who only need the interview, I recommend talking to the TA before lab and say, hey, I'm only here for an interview, I'm not taking the quiz. Can you maybe call my name first? And they can get you out of there. They should accommodate you, they should call your name first, and then get you in and out. Or else you're just sitting there staring at the wall waiting for them to call your name on the interview. So don't hesitate to just ask them, hey, can I go first? And they might say something like, well, somebody else already asked to go first in your same situation, but you can go second. And you'll be like, cool. And then you can get in and out a little bit quicker. So that's lab this week. Expected deadline coming up. Any course logistic or any issues that are out there that need to be discussed? For those of you waiting on email, I am still a few days behind on email. Tuesdays, I try to keep wide open. Tuesday's my catch-up day. So if, by tomorrow, you should definitely hear from me if you're waiting on an email. But, anybody have anything else? Otherwise, I'm just going to talk about trees. Let's talk about trees. If you don't see these dark mode slides, by the way, just refresh the page. I changed the file name for the slides. So you might have reference to the old thing. All right. I'm talking about trees then. Specifically, how about for LO1 interview? Yes, that's in my boat right now. Either tonight or tomorrow, I'll reach out to you about LO1 interviews if you're still in that boat. There are a small handful of you in that, and I'll reach out to you. I've been trying to carve out time in my schedule for those interviews. I think it's going to end up being an evening thing. I think Wednesday and Thursday evening I'm going to open up for those interviews. And since it's in the evening, it'll probably be on Zoom. I haven't finalized that yet, but I just got no time in my schedule to put a big block of interviews. Not big, it's not, it's hours though. It's hard to find that time block. But that is coming, I have not forgotten. That is coming up. All right, so let's talk about binary trees. So last time, and I'm going to start by talking about linked lists. Last time we talked about linked lists. Linked lists are built on nodes, and each node has a reference. Each node has its value that it stores at that node and a reference to one other node, and that's a linked list. With a tree, we have nodes that know the value stored at that node and references to two other nodes. And that's the difference. Other than that, they're structured just like linked lists. We're working with nodes, and nodes have references to other nodes, and they have values, but we can have two references instead of one. Very, very small change to the structure of a node with significant ripple effects to how the overall structure of a binary tree and also how we work with binary trees. All the algorithms we have for linked lists are pretty much out the window now that we have two references instead of one. So these references, we call them the left and right references, or just a little bit of vocab. I'm never too big on vocab, but a few vocab words that I will use throughout these lectures is child and parent nodes. So we have references to a left and right child node, and to those child nodes, the node referring to them would be their parent node. And if you do go into trees, these are the only two words I'll use for this analogy. But if you go into trees, if you start studying trees and studying algorithms on trees, or especially if you do like research level work on trees, this analogy extends as far as it can. So you have grandparent, grandchild nodes, niece and nephew nodes, descendant nodes, where a node, if you follow the left and right references in some order, you'll eventually reach that node. That's a descendant. The whole thing applies, the whole family tree analogy. So if you do get into trees, you can look forward to that. I'm going to use parent and child, are the only two that I'm going to use that are applicable to 116. That's all I need for 116, I should say. We don't need to get more complex than that when it comes to trees. Of course, in 250, you will get quite a bit more complex, and then in 331, even more so. But in 116, we're going to keep it as simple as we can. So here's a visual of a tree. I'm going to draw this in a little bit different way. I drew some linked lists using this not syntax, this structure. It's a way of representing them. We're going to look at this for a little bit. A tree, just like our linked list, wasn't actually a reference to a list. That's the way we think of it when we have a scholar list. We think of that as a reference to a list, but it's not actually. What it is a reference to the first node in that list, which we call the head of the list. So we have a reference to the first node, and that's it. And then through that reference to that node, we can find a reference to the next node, where we can find a reference to the next node, we find a reference to the next node until we reach null, and we reach the end of the list. A tree is similar. We only have a reference to one single node, and that is our reference to the tree, and we call that node the root of the tree. So we have a reference to the root node, and that node can have references to other nodes and its left and right children, which can have references to other nodes and its left or right children, and left or right can be null if there is no child node for that left or right reference. And once we hit these nulls, that's when we know the tree is over. But it's not just one null like a linked list. We just read null once, we know we've reached the end of the list, and that's it. Fairly straightforward structure. With a tree, it gets a little more complex, that we're going to have nulls for every, what we call, branch of the tree. Yes, there's the physical tree analogy as well, roots and branches, leaves. I'm not going to say leaves in 116, except just now, though. Since I did mention it, a leaf would be a node where, with no children. Left and right are both null. But I have a reference to the root, and each branch of the tree, which is a path of references that I can take, every branch eventually has to end in null, or else you did something wrong. For example, if left here was a reference to the root, I would have an infinite tree. It's not technically a tree at that point. Everything gets all busted. But eventually you're going to reach null as you go down the tree, as you follow the references. This is the tree I'm going to use, for example, in this lecture. I like this because it's nice and symmetric. It's what we call a balanced binary tree. But these trees can be imbalanced. So don't fall into the trap, but I see this mistake in students' code all the time. Don't fall into the trap of assuming that if left or right is null, then the other one has to be null. Some of my examples, I do that just because I like the nice symmetry on the slide. It just looks prettier. up on the projector. But right could be null, where left refers to a node, or left can be null and right refers to a node, or left and right are both null, or left and right both refer to a node. So there's 4 different situations that you can be in when it comes to references to nodes or null. All 4 of those situations are valid. Don't get into the trap where either left and right are both references to nodes or they're both null. These can be what we call imbalanced trees like this. And in fact, the tree that you get in task 2 when your method is called is an imbalanced tree. It's not a balanced tree. No. It's kind of true. It is true, but I guess not to the point that I'm saying right now. But again, this is the tree I'll use for today's lecture. It's symmetric. I just think it looks better up there. In the code, this is it. This is how we're going to work with our binary trees. This is the binary tree node class. Again, it's going to take type A, so we can build binary trees that store any type of information. In task 2, you're going to get a tree of decision tree nodes, which are going to have a couple of methods that you can call to decide how to navigate that decision tree. Here in this example, we just got ints. So each node has a value of the type parameter, a left reference to a binary tree node of the type parameter, and right, again, of the binary tree node of the type parameter. So we have 2 references to other nodes and the value A. And unlike our linked list node class, we're not going to expand this at all. This is what it is in the repo. It's just the constructor, and that's it. We're not going to add any methods to this class at all. We're going to write some methods to work with trees. We're going to write some algorithms to work with trees, but they're going to be external to the binary tree node class. They're going to take a node as a reference, as an input parameter, and then work with that node instead of writing any methods in here. So this is the whole structure of our tree, and that's it. We're done. Done with that class forever. You can add methods to it if you want to expand the functionality, but I'm not adding any methods to this class. That's the whole class that I'm going to give. So to create these binary trees, to create the structure, this code, by the way, is going to build the binary tree from the previous slide. We're going to create them more manually. So with a linked list, well, we did create our linked list manually like this too. We prepended manually. But we're not going to write any insert or delete methods in the binary tree node class, so we have to do things manually. We're not eventually going to be able to call append or prepend. We're going to do this manually. So I'm going to create a root with the node with the value 5 and references null, null. And I'm going to manually override those nulls with new nodes that I'm creating. So I'm going to say the root's left child is going to be a new node with the value 2 and child nodes of null, null. The root's right child is going to be a new node with value 8 and children null, null. So after these 2 lines, this line replace this null, this line replace this null. I'm starting to build out this tree 1 node at a time. So when I create the root node, I'm creating a node with value 5, a reference to null, and a reference to null. And then when I add that left child, I'm saying root.left, which is null at that point. I'm going to set that equal to replace the null with a new node with value 2, left of null, right of null. So I'm manually replacing those nulls as I build out the tree to eventually get this tree. The nodes right.left equals a new node of 7, null, null. So the root.right.left is a new node with 7, null, null. So that's how this code is manually building that tree from the previous slide. When we get to binary search trees on Wednesday, we will actually write an insert method, but it won't be part of the binary tree node class. Just as a heads up, just in case you get to Wednesday and say, you said we weren't going to do insert. We will do insert, but not in the binary tree node class. In the last lecture at this point, because I'm about to go into algorithms, just like linked lists, I don't have a whole lot to say about the structure of a tree. So if anybody has questions about the structure of a tree, please ask. In the last lecture, somebody asked, why the hell are we learning trees, which is a completely valid question. So I wanted to say the answer that I had there and just go over some examples. They didn't word it like that, in case you're wondering. That's my wording. They said, what would be a real-world application of a tree? They asked it much more politely. So I want to go over a few applications. And so one of them is expression trees. I used to do expression trees in 116, and nobody liked it, and it was confusing, so I stopped doing it. But I'll very briefly talk about it, and I left the code in the repo. It does use first-order functions, which we don't talk about anymore. So since I'm not using it in lecture, I didn't revise it to not use first-order functions like I did the rest of the code. But with an expression tree, if you're curious, the code is in there, where each node can either be an operator or an operand. So for example, this node might be plus the addition operator. This node might be, I'll leave it at 2. This could be 2. And then this would be, say, division, and then 7 and 14. And then to evaluate that, you would evaluate the operator or operand at each node. So operands would just return their values, and then operators would take their left child, operator, right child. So it would be 7 divided by 14. We'd get 0.5, and then 2 plus 0.5, and the expression tree would evaluate to 2.5. And it's a way, I don't know the exact details of how it works or why it works. I know how it works, but not why. But I'm told compilers like to use these expression trees when parsing your math and your code to be able to represent equations in trees, and I guess it's more efficient that way. I don't know. I don't know the details. But I'm told that's where expression trees are used. The nice thing about expression, we haven't talked about the things yet, but the nice thing about expression trees is, I can't talk about that yet because we didn't talk about traversals. When we talk about traversals, I'll revisit that. Another application of trees is for your homework. We're using trees for a decision tree. Your AI has a decision tree of nodes, and that decision tree is going to ask a few things. I forget what I said is right or left, so what I say might not exactly be what's in the repo. But the root node is going to be a decision node, which is going to check how close the closest player is. And if that closest player is really far away, I think I put 10 units is really far away, then we're going to branch right, else we're going to branch left. And at the right node is going to be an action node which says stop, just don't move. If the closest player is really far away, just don't do anything. You're in a stopped state, so to say. Not state as in state pattern, but that player is going to stop. If the closest player is kind of close, we're going to make another decision. Are they close enough to be in firing range or not? If they're not close enough to be in firing range, then we're going to hunt down that player. We're going to try to get closer. And if we're already in firing range, we're going to fire at that player. So your AI has 3 different actions it can take. Just sit there and do nothing, hunt a player, hunt the closest player, or fire at the closest player. And the decision tree decides which one of those 3 actions it's going to take by deciding how to navigate that decision tree. So each node, you're going to ask a question. I forget what I called the methods. I think it's check. It's going to return an int. And if that int is negative, that's your cue to navigate to the left child. If it's positive, that's your cue to navigate to the right child. And if it's exactly 0, that tells you that that node is an action node. So for example, if the closest player is really far away, you're going to call check. It's going to return a positive value. You're going to navigate to the right. That's going to return 0. So you know that's an action node, and you're going to return the action at that node, which is going to tell that player to stop. So your goal for task 4 is to navigate is to navigate that decision tree. So that's an application. This is fairly common in AI to have a decision tree like that. And my last real-world application, that's the application of trees besides binary search trees, but I'm saving that for Wednesday. We'll talk all about that in a whole lecture. My last application is, if you ever played the 20 questions game, you have the game, it's going to ask you a question, you're going to think of something like, it says, think of literally anything, and I'll think of like dog, because I can't think of anything more interesting. And then it'll say like, is it living? I'm going to say yes. Is it a mammal? I'm going to say yes. And then it's going to ask me some other questions. Is it bigger than a refrigerator or something? I'm going to say no. And it's eventually going to get to a point where it's going to say, you're thinking of a dog. And I'm going to be like, holy crap, how did it do that? With a dog, it's not as impressive. But you can think of just about anything, and those games will get down to what you're thinking of in usually 20 questions. Sometimes the game asks a few more questions. It's like, oh, I didn't get my guess in 20. Can I get like 5 more questions? And I think it usually does that when I answer a question wrong, because sometimes I just don't know. I don't know the answer. But how those work is with trees. So it's a binary tree where the root node is going to be a question. And I think the games usually randomize the first question. I don't remember. But the first question, if they just build their binary tree, first question should always be the same every single time. It'll be the root of the tree. I think maybe they build multiple trees and then randomize which tree they use just to switch things up a little bit. It's just more fun to play if the first question is different every time. I don't know. But once they have their tree, they're going to ask a question. You're going to answer yes or no. If you answer no, they're going to branch one way. Yes, they're going to branch another way. And each node is going to have a question that's going to ask you, and it's going to continuously navigate through this tree until it gets to a node where left and right are both null, or however they represent in their code. In our example, it would be left and right are both null. That would indicate that that's an answer node. And then that node, whatever that node says, that's what you're going to go back to the player with and say, you're thinking of a dog. And that's how those games work, is with these binary trees, where each node is either a question node or an answer node. It's very similar how your homework works. Each node is either a decision node or an action node, and they're deciding whether you need to navigate further down this tree, or if you're at a node that determines what this AI character is going to do. Yeah? Yes. Yes, exactly. So, I got some questions for you about that. So this node, the height of a tree node, this tree, I don't know how I'm wording this one, but this tree is height 3. 1, 2, 3, there's like 3 layers to this. I wasn't ready to define height. In the last lecture, I just started saying height without defining it, I think. This has height 3. Whatever the height of your tree is, the number of nodes is going to be 2 to the height minus 1. So I have a height 3, 2 to the 3 is 8, minus 1 is 7. I have 7 nodes in my height 3 tree. If I have a height 10 tree, how many nodes would I have in that tree? How many nodes could I have? Nobody answered me in the last lecture either. I waited like a full minute too. I don't know if I'm going to wait a full minute this time. Yes. 1023. Yes, thank you. 1023. So you can have over 1,000 nodes in that tree if you have height 10. So if you had 10 questions in your game, 1,000 nodes. We go all the way to height 20. You got your 20 questions game. Or actually it'd be height 21 because it's 20 questions and then your answer nodes at the bottom. Height 21, how many nodes do you have there? Yes, over 2 million, which means your bottom row of just your answers, you got 1 million answers in there. So your 20 questions game, just answering 20 questions and navigating down a tree of height 20, has 1 million answers in it. So when they're developing that game, however they crowdsource their information, because it's got to be a lot of work to actually get the data set together. Maybe they use Mechanical Turk or something, I don't know. But somehow they probably crowdsourced that, or they had one poor soul sitting there answering these questions for a million different things. But they can ask people to think of literally anything. You ask enough people that, like if you're on Mechanical Turk, that's Amazon's like crowdsourcing thing. You pay people like 1/10 of a penny per answer, and you can get 1 million answers from people who are just bored at work trying to make an extra $1. You can crowdsource that, take the top 1 million answers that people gave, and those are your answers. Those are the things that you can think of that is going to answer. So if you're playing this game and you think of one of the 1 million most common things people think of when they're asked to think of something, the game's going to work. It's going to get to the thing that you're thinking of. It's got 1 million things that you can think of. You got to really try to think of something that's not in there. And then with those 1 million things, then it's time to build the decision tree. They have to build all the questions, where ideally each question splits the remaining search space in half. So each question should get rid of half of the answers. If you have a nice balanced search tree, a nice balanced binary tree, I ask one question, I go from 4 possible answers to 2. I ask another question, I go from 2 to 1. If you start with 1 million, you're going down to 500,000, 1/4 1,000,000, 1/8 of a million, so on, until you get down to just one answer. After dividing 1 million by 20, 1 million by 2, 20 times, you get down to a little bit less than 1, because it's a little over 1 million. And that's how that game works. It's a big old tree of height 20 or 21. And then it builds all the questions of that tree to be able to get down to those answers. And then a bit beyond the scope of the example, maybe beyond what I feel like explaining right now, but to build that tree, you would build feature vectors for every single answer, every single one of your 1 million things. You have all of the questions that you want to ask, and you would answer all of those questions for every single one of those 1 million things, and then have an algorithm to be able to build your search tree. The tree itself will be built algorithmically, but you need the data to put into it. You need 1 million things and the answers to all your questions and answers to all those questions for each one of these things that people can think of. That's the feature vector for that thing, and then you use those feature vectors, throw all those in an algorithm that's going to build your tree as balanced as possible, so it's depth 20. You don't want a certain thing. Well, if you think of this thing, then you have to ask 30 questions. Like, that defeats the purpose of the game. You want it of depth 20 questions. So anyway, those are my real-world applications. Kind of like Akinator. I'm not familiar with what it is. But I'd have to assume it's a 20 questions game. We're just asking you a bunch of yes or no questions, and then guesses what you're thinking of. If it's like that, then it's exactly what I'm saying. How are functional trees like this for memory and processing efficient? I know it's like a 250 topic, but still. So I don't really know. Like, that's the limit of my understanding of those. I think it's for processing when it's tokenizing an expression, but my understanding of it's a little weak. You describe them using if statements too. That might be a bit much. You describe them using if statements too. Generally, there are a lot of approaches to writing code. I'll answer this with a little bit of a generic answer, but pretty much any code you could rewrite using polymorphic code. It's just a question of, is it the best idea or not? But you could do the same thing using polymorphism. Yeah, exactly. And I don't know, I'd have to look to see what the probably know and definitely know, how exactly they implement that. But if your answers are only yes or no, then binary tree all the way. Okay, so that's the structure of a tree and some examples. But that's the structure of a tree. It's a node that has a value and two references, left and right. But how do we do anything with these things? So for today's lecture, I want to talk about traversals. We're going to talk about three different traversals: pre-order, in-order, and post-order. They're all pretty much the same. You're learning one concept here, the idea of a tree traversal. And we want to know how to run these traversals. For these examples, I just want to print the value of every node to the screen. That's all I want to do. It's a nice modest goal. But we have a challenge here because, like with a linked list, for example, this was easy. Or with an array, you just go down. It's a sequential data structure. You just go down the sequence and print out everything with every value. With a linked list, you start at the head, you print out its value. You go to its next, you print out its value. You go to next, you print out its value. You just do that until next is null, and then you know you're done. You know you printed everything to the screen. Done. Easy peasy. A little complicated, but not overly so. We did have to spend a week talking about it. But not as complicated as trees. With trees, it gets a little tougher because you have two references. Where do you go to call the next node? Like, how do you visit the next node? Do you just always go left? Do you always go right? Obviously, neither of those are correct. You have to have a mix of those. And when do you know when you're done? You can't just go till you hit null. In the tree for today's lecture, we have 8 nulls in there. We're not just going to end once we see one of them. So we got to navigate this a little more carefully to make sure we visit every single node and make sure we don't visit a node twice. And by visit, I'm going to say the word visit just by force of habit. When I say visit, for today's example, I just mean print to the screen. Can a tree be more than binary? Yes. Why, yes, it can. So we're talking specifically about binary trees, meaning they can only have up to 2 child nodes. Ternary trees can have up to 3 child nodes, or you can just have trees in general, which can have any number of child nodes. But specifically binary trees, the bi meaning 2, up to 2 children. But yeah, you can absolutely have trees. The other example that a student gave in chat was a file system. So if you have your file system that has the root directory, which can have subdirectories and files, that's a node, a tree node with children that can be other directories or files, which would be like a file would be like a node having 2 references to null or no references to any children, I guess. And then each directory can have as many children, child directories, subdirectories, and files as it wants. And it's all one big tree structure, starting with your root drive, your C drive in Windows, or what is it even called in Mac? I've used Mac, and I don't even know not my computer, whatever it is. But whatever the root is, my Mac, maybe? Whatever that root is called. Or is it just slash? I guess it doesn't have drive letters. It would just be slash, like any other Unix-based system, I suppose. But that would be another tree. That would be a non-binary tree, is your directory structure on your machine. All right, so let's look at some code. Here's an in-order traversal, and the code's going to be actually pretty simple. Recursion is going to help us out a lot here. Recursion is going to do most of the work, and our code isn't going to look much more complex than our linked list navigation code when we wanted to just visit each node in a linked list, just printing all the values of a linked list. It's about as complex as that. So for in-order traversal, we're going to call this with the root node of the tree that we want to print. Our base case is going to be calling this with a node of null. So if the tree itself is empty, root is null, or when we visit a node that's null, or when we tried to visit a node but that reference was null, that would be our base case as well. Then we're going to do nothing at all. So if the node's null, this is false, and we're not doing anything at all. This method returns unit. We're not responsible for returning anything. We're just doing absolutely nothing if the node is null. If the node is not null, we're going to make a recursive call on its left child. Then we're going to print the value of this node to the screen, and then make a recursive call to its right child. And that's an in-order traversal of a binary tree. Pre-order traversal, it's almost the same code. but we're going to print the node's value first and then make our recursive calls. Post-order traversal, you guessed it. We're going to make our recursive calls and then print the value to the screen. So the difference between these code-wise is almost nothing. We're going to make the two recursive calls no matter what, and no matter what traversal we have. And our only question is, when do we visit this node's value? Either before the recursive calls, after the recursive calls, or right in the middle of those recursive calls. We only have 3 choices, so we have our 3 traversals: pre-order, post-order, and in-order. We're going to focus on in-order. That tends to be more useful, at the very least more useful for the application we'll see on Wednesday of binary search trees. The other 2 do exist. I want to make sure I let you know that they do exist, but we're not going to look at them in depth in 116. One of the big reasons to still mention them is, for whatever reason, I said the same thing about linked lists, the same is true for trees. For some reason, interviewers love to ask about these. And by interviewers, I don't mean your TAs within 116. Obviously, they're going to ask about linked lists, trees, and graphs during the LO3 interview. I mean job recruiters, or sort of job interviews for internships, for full-time jobs. For some reason, they like to ask about these things. I can speculate why. I think they like asking about linked lists and trees because they know that you've been taught this stuff. Any CS curriculum out there, any university you go to, they're going to talk about linked lists and trees. So the recruiter knows that that's a good question, good questions that they can ask to tell if you paid attention during the curriculum. I think that's why they ask that, because they know you were presented this information. They could also ask about OOP and polymorphism for the same reason. There's not going to be a computer science curriculum out there. No university is going to let you go 4 years without knowing about these things: linked lists, trees, polymorphism. They're pretty fundamental, just computer science topics. And then there's a kind of a circular feedback loop. Since they always ask about it, we also have to always continue teaching it. We don't really have a choice. We have to teach these. Even if I'm not going to do anything with pre-order and post-order, which I'm not, I still have to mention them because you might have it as an interview question. I don't want you coming back to me saying, why the hell didn't you tell me what a pre-order traversal was? And I'll be like, because it's dumb. You're never going to use it. It's not entirely true, but so let's see these things in action. Here's the code, all 3 of them. Pretty simple code-wise, but let's go through the run of an in-order traversal on this tree that we've been working with, and I will come back to that. There is one example of a pre-order that I'll give you of why that would be interesting. And I'm going to change the way I represent the tree just so we don't have all that clutter on there. My nulls are just going to be boxes, and I'm going to get rid of all the notation for the references just to make this a little bit cleaner. So we're going to call this on the root. We have a variable root with a reference to this node, and we're going to call this method on this node. So we're going to call the method on this node. This node is not equal to null. So when I make this call of root, node is a reference to this node, not null. So we're going to make a recursive call on its left child. So we're going to go to the left and make this recursive call. And my stack frames here, I'm not going to do the whole memory diagram in this example. I'll save a memory diagram for Friday. But my gray boxes, those are going to be stack frames that are on the stack but are inactive. And my green boxes, those are going to be there can only be one. That is going to be the active stack frame that's on the top of the stack. And we're going to see these stack frames pile up. We're going to see the actual stack data structure, the concept of a stack in our stack frames. So 2, not null. This node containing the value 2. The node is not null. It's a reference to a node with a value and 2 child nodes. In-order traversal, recursive call on its left child. We get to this node. It's not null. We're going to recursively call in-order traversal on its left child. So we're going to get a call of in-order traversal of null. So node does equal null, so this is false. So we skip the conditional, and we're right at the end of the method. We just don't do anything. We've hit our base case of null. Don't do anything. That returns back to this stack frame. So we have 4 stack frames on the stack right now. This is the top one, second one, third one, fourth one. And we can only modify, we can only remove the top frame from the stack because it is a stack, the data structure, the concept of a data structure. And we can only add to the top of the stack. So once we pop this off of the stack, when it returns, we go right back to this as being the top of the stack, and that becomes the new active frame again. This frame was sitting right here on this line of code, waiting for this recursive call to return. That recursive call just returned, so we can move on with the code. Print line node.value, get -3 on the screen, and then make our write recursive call. Our write recursive call is null. There's nothing to do, so it returns back to this stack frame, which was waiting for this recursive call this time. We jump back, we resume to where we were in the code. Each frame remembers where it was when it created the next stack frame. So it was right here, that's the end of the method, returns, gets back to this stack frame, which was sitting right here. It just got its return value returned from its left child. So it knows to print itself to the screen and make a recursive call to its right child. We get 2 to the screen and go over to the right. This node's going to make a recursive call to the left. That's null. It returns without doing anything. Print 4, make a recursive call to the right. That's null, does nothing, returns. This stack frame is done. It returns. This stack frame was waiting for its right node. It's done. It returns. And we go all the way back to the root node, which was waiting for its left node to return. Its left node returned. It's going to print its value and then make a recursive call on its right child, which is going to be that node containing 8. Which is going to make a recursive call to the left. 7 is going to make a call to null, print, null, return. 8's going to print, go to its right child, null, return, print, null, return, 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 return. And we get every value printed to the screen. No duplicates, we didn't miss any. We're going to hit every node in this tree and print out all of its values. Yes?
So, I observe as a problem with this approach is that the order in which things come out of the tree is very. What would be, I guess we would have to write another method understanding of the particular organize it into something that makes sense.
Yeah. So the comment is the order seems kind of awkward. Like, why do we print things in that particular order? It seems kind of arbitrary, and it is kind of arbitrary. So the idea is for your specific application, for whatever structure you have your tree in, you would pick which traversal order you want, and pick the one that's going to make the most sense for that application. And you can change, like, even though we have these 3 traversals, you could also switch it up a bit and make the right recursive call before the left recursive call and navigate this thing in reverse order. So it's deciding how to traverse your tree in a way that makes sense for your application. The way we're going to use in-order traversal in Wednesday's lecture is on binary search trees. This tree was carefully chosen to satisfy the condition for a binary search tree. And you'll notice that we ended up printing the values in sorted order. And that's going to be one of our features of an in-order traversal that's going to pay off for us for binary search trees. We got all these that lag. All these are in sorted order. So it was carefully chosen to show that. And I'll show why in Wednesday's lecture. That doesn't just always happen. I carefully created this tree just so it would have that property. But if we use a different traversal, we're not going to get that property. So if I use a pre-order traversal, we're going to print, recursive call, print, recursive call, print, recursive call, return, print, return, 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 print, print, return, print, return, return, return. And we get a very different order with a pre-order traversal and with a post-order traversal, and of course neither of these are sorted. Recursive call, recursive call, recursive call, recursive call, print, return, recursive call, print, print, call, print, 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 print. So we get very different order depending on which traversal we choose. And that's why we would choose different traversals over the others, is what order do we want. Now, if we have an expression tree, I promised I'd come back to the expression tree. With an expression tree, if I do an in-order traversal, I'm going to print out my equation in infix notation, which is how we're used to seeing equations. We would have to modify this a little bit to add parentheses in here to make sure we don't lose our order of operation, but we would get things in the way that we're used to seeing them. Or we can call it in a prefix traversal, and then we'll get the expression in prefix notation, which is a way that's easier to write code for computers to evaluate expressions, though it's not very human-friendly unless you're used to looking at prefix expressions. But depending on which one we choose, we can get our expression printed in a variety of different ways. So we wrote these with recursion. And for you naysayers out there who are like, I've never learned a recursion, it's stupid, I'm going to use loops for the rest of my life, I'm going to live and die by loops. Here's where we're seeing the payoff of recursion. If you don't see the payoff of recursion here, the code here is quite simple. It's 5 lines of code, and one of those lines is a closing brace. If you're a naysayer on recursion, I challenge you to rewrite any one of these 3 without recursion. So far, nobody's taken me up on this challenge. Nobody's come to me, especially nobody's come to me and said, oh yeah, I wrote those without recursion. It was super easy. Like, it was not a pain in the ass at all. Write these without recursion. If you are going to take me up on this challenge, one tip is the memory stack is keeping track of a lot of information for us. It's keeping track of one specific piece of information, the stack itself. And there's 3 different times we visit each node. The first time, for an in-order traversal at least, the first time we visit a node, we're making a left recursive call. The second time we visit a node, we're printing and then making a right recursive call. And the third time we visit a node, we're returning and just being done with that node. So if you're writing this without recursion, you have to keep track of each time you visit a node, which visit number is this, like which visit is this, and if it's the third visit, which node do we go to next? You have to remember all this, and if you use a stacked data structure, you'll want to use a stacked data structure to get that done. And that stack is going to be storing all the same information that the memory stack is storing for you. So if you do want to take me up on that, there's your hints on how to get started with it. And with that, have a great day. I'll see y'all Wednesday.